Okay, so on Monday, we had started looking at very simple circuits. For the time being, what we did was we were looking at a battery connected to whatever device you have. The battery essentially provides a constant potential difference. So let's say V. And then we said that the V, experimentally, it's observed that the potential is proportional to the current, or the current running through the battery, through the circuit, is proportional to the potential. The higher the potential, the larger the current will be. And the proportionality constant, we called it the resistance of the circuit. So this is the resistance of this circuit over here. Now, in general, you can have resistors of arbitrary shape, but usually we will be considering systems, materials made in the form of more or less a cylinder. And it is again experimentally known that this resistance is proportional to the length of the object and inversely proportional to the area of the object with a proportionality constant that we call the rho. Rho is called the resistivity. And inverse of rho is defined as the conductivity. So basically what happens is, if you connect a battery to a circuit, the battery creates an electric field inside the conductor. And the electric field is inside the conductor. So if you have such a conductor, a long one, you connect this to a battery. And we know that there is a potential difference between these 2 points. VAB will be equal to R times whatever current is running through it. So if there is a potential difference, remember the potential difference is defined as the integral of the electric field minus E dot dl from B to A. So if there is a potential difference between 2 points, it tells that at least in certain regions between those 2 points, there should be an electric field. So in this case, it is inside the conductor, and it is more or less parallel to the conductor surface. So in a sense, the conductor traps the electric fields inside. Well, most of it, not all of it. So we have an electric field created inside. Now, this electric field will push the electrons. Well, it will also push the nuclei, but the nuclei are at rest. But it's the electrons in a metal, at least, that will be moving. So since there is an electric field, it will exert a force on the electrons, which are free to move. So they will be moving freely and hence create the current. So the electrons will be running in this direction, whereas we call the current is to be in the opposite direction. So the electrons inside the metal, they will be moving in the opposite direction to the electric field. Then they will come to the battery, and what the battery will do is it will just move that electron from a low potential energy to a high potential energy. So again, the electron here is at a higher potential energy, so it will just flow through it. And while it is moving through this piece of wire, the number doesn't change, but the electron will be colliding with the nuclei, with the material making your wire, the cylinder, your conductor. So during these collisions, it will lose energy on one hand. On the other hand, it will gain energy due to the electric field. So typically, they will balance. So how much it gains from the electric field, from the force, it will lose due to these collisions, and that will be the energy. It will heat the resistor, and that will be dissipated as heat energy, or depends if you have not these LED lamps, but the old type of lamp. In the old type of lamps, the material will be heated up, so it will start emit light, and so you have the lamp. Or in more complicated circuits, the electron, as they go, they will be colliding with the material, but they will also be creating a flow of energy, and it will do all kinds of other stuff in the calculators or in your cellular phones, etc. Now, of course, this battery, when the electron reaches this end, it is at a low potential energy. And the battery just pushes up to the high potential energy. And so essentially the battery will be doing some work on these electrons. And the power of the battery, which is defined as the work done per unit amount of time, well, the work done is V times, if you are moving a charge delta Q over a potential difference V, the total amount of work that you do is V times delta Q. From the definition of power, you divide it by delta T, and this is V times I. This is the power of the battery. This is which means it's the rate of work that the battery does. It is also power of the resistor. It is the rate at which it kind of dissipates energy. It heats up, for example. And you can, just using V is equal to I times R, you can write, we wrote it in different forms. It's V squared R, I squared R, or V squared over R. So this was more or less what we had discussed on Monday. Any questions up to here? One more thing, we said that this resistivity actually depends on the temperature. 1 plus alpha times T minus T0. You can write that with temperature it will change. And if you know it's the resistivity of a material at a given temperature, at temperatures close to that temperature, reference temperature T0, you can just write the change like this, where this alpha is just the known coefficient based on the material. So if you want to make a thermometer, this is one way of making the thermometer. Just make a device that measures the resistance of a material. So any change in the resistance of the material will be due to the temperature. And so you can determine what the temperature of the environment is. So such a thermometer can work up to thousands of degrees Celsius.
Is that constant?
This one, not a constant exactly. It also changes with temperature. But in certain ranges, you can assume it, certain temperature ranges, let's say, you can just assume it to be constant. Or you can just look up the tables on how that changes as a function of temperature. Other questions? Now let's see how the current is actually created inside our conductor. So we said that, okay, if you just enlarge your conductor, inside you have the electrons that are free to move. Well, you see, on the average, no, not on the average, but the electrons inside conductors, in general, they move quite fast. I mean, their speeds would be comparable to the speed of light. But the thing is, let's say you have this electron. It will, let's say, it's moving very fast in this direction. Then here it will collide with something, with the nuclei, with other nucleus, with other electrons. So it will make a collision. But if it makes a collision, it will just change its direction. So it will be moving in this direction after the collision. Then it will come here, and then it will just collide with something else, some other atom over there, some other electron. It will just scatter in a different direction, so it will just move back and forth. In general, the electron, although it's moving very fast, it's just moving in random directions. So it will be just at rest without the electric field. But if you exert an electric field by connecting this to a battery, so what will happen is, if this is my electron at a given point, again, it will move more or less randomly. It will move in this direction, collide, move here, come here, move here. It will just make this random motion. But on the average, the electric field will just push it in one direction. So although it will be, let's say, it won't be going straight, it will bend slightly and make a collision. After the collision, we can say that on the average, it will just scatter to a random direction. So it will scatter to some other direction, but that direction will also bend. So in a sense, just take all these trajectories over here, they will all bend in that direction. So that will create an average shift in the position of the electron. So if the electron starts over there, let's say it starts, over here, then when it moves, it will move randomly here, just up and down. But on the average, it will be shifting to one direction, determined by the electric field. So you see the electron started over here, still doing random motion more or less, but it's kind of shifting in this sense. So eventually the electron will move to the other end of the conductor. Now this speed is called what we call the drift velocity. So this electron will move, the average position of the electron will move in that direction with what we call the drift velocity. Well, we can estimate the drift velocity by relating it to some current. Suppose we know the drift velocity. Now, how can we calculate the current? What was the definition of the current we had? Let's start from the simple definition of the current. What was delta Q? What is delta Q? Charge? What do you mean by charge flow? What do you mean by change in charge distribution? What does it mean? How do you? Yeah, number of charges. You see, you just take this cross section, let's say. You just count how many charges pass through that area. Well, let me use the positive notation. This is delta Q. So how many charges, positive charges, pass in a given in the direction of the current per second? Well, let's just fix the delta T. Now, on the average, the electrons are moving with this speed. So within a time delta T, how far away will they move on the average? It's just the drift velocity times delta T. So let's say it is this length over here. So all the electrons in this volume within this time delta T will just cross this point. So that is my delta Q. So I'm just connecting my conductor to a battery. It is creating the electric field. It will be pushing the electrons to one side, if it's a metal. If it's a solution, it will push the negative ions to one side, positive ions to the other side. But let's stick with the metals. So all the electrons within this volume will cross this area. So the positive charge crossing that area will be just minus the total charge over here. So if, let's give some definitions. Let me call N is the density of charges that are free to move. You see, if you take an arbitrary metal, it will be neutral. But I don't really care about the positive charges, because what will create the current will be the electrons. So this N is the density of the electrons in that case. So if that is the density, what is the total number of charges here? Let's say this is the number density. In terms of the density, the total number is the density times the volume. Let me just separate out the Q, or E. This is the charge of minus E is the charge of an electron. So density times the volume gives me the total number. If I multiply it by the E, it gives me the total charge, divided by delta T. This is E, and well, the volume, this you can think of as a cylinder. The area, the cross-sectional area is A, the height is Vd delta T. So the current is actually E, the charge of the charge carriers, multiplied by N. N is the number density of charge carriers times Vd times A. Any questions here?
Can you explain one more time the volume? Can you explain one more time the volume?
The volume. Well, what we are interested in is, given a time delta T, how many charges passes through this area. So on the average, the electrons are moving with a speed v times t, their drift velocity. So in a time delta T, they will be moving this much. So all the electrons within this volume will cross this area in a time delta T. That is the delta Q. So we are looking for the current, and which we define as the charges passing through an area per unit time. So all the charges in this volume will cross that area, so hence contribute to my charge, to my current. So then I need to calculate what is the total charge here. Well, the total charge here, I'm not really interested in the total charge, but I'm interested in the charge that is creating the current. So in this case, it is the electrons. I define N to be the number density of charges. In this case, it will be the electrons. So the total number of charge electrons here will be the number density times the volume. It's the number density times the volume. And this is the number of electrons I have. Just multiply by the charge to obtain the total charge crossing that area. Well, that the volume, it is more or less a cylinder. The volume of a cylinder is cross-sectional area multiplied by the height. So A, the height is V times delta T. This is my A times V times delta T. This is my volume. So delta T's, they just cancel. And hence, I have the current is given by the charge density. So if a material has a denser charge carriers, it will be a better conductor. The drift velocity and the area. Now the drift velocity is proportional to the electric field. Now you should object to this one. If the electric field determines the force acting on the electrons. And the force, according to Newton, determines the acceleration, not the velocity. But the drift velocity will still be determined by the electric field itself. You see, the electrons are moving very fast. And so in a very short amount of time, they will make many collisions. Within that very short, between two collisions, at the end of every collision, you can just imagine that the effect of the electric field basically disappears because it's just scattered randomly. It just loses a random amount of energy, etc. Now, but between those, every collision, since the time interval is very small, its velocity, its acceleration might be large, but still, since the time interval is very small, its velocity changes by a very small amount. You see, we will just do some estimates. The velocity of the electrons are typically of the order of 10 to the power 6 meters per second. And the drift velocity is typically 0.1 millimeters per second. It's just a very small shift. So in a sense, this is the average value. You see, the speed of the electron changes from this much to this much plus 0.1 millimeters per second. So you don't really need to care about that. It changes from this one to that one gradually, but just a definite shift. So that is why the drift velocity is on the average proportional to the electric field itself. Because what we are really interested in is the change in the average change in the velocity. The average change is just some constant. So if we say that the drift velocity is proportional to the electric field, the current will be just E times N times the drift velocity. Now let me not call this sigma, let me call this some constant alpha. Drift velocity is just alpha E times A. Or this is E times N times alpha times electric field is the potential difference divided by the length of the object. And finally, the current is just E times N times whatever this alpha is, A over L times V. But remember, the current running through our resistor was always proportional to V. That is what we already obtained. And the proportionality constant was defined as V over R. So now we have an interpretation of why we have those resistance. And R is given by 1 over E n alpha L over A. And remember, this we had defined as 1 over sigma L over A. So that constant alpha is essentially given by the conductivity of the material. Well, the conductivity depends on whatever that alpha is and the number density of the charge carriers. Now let's do an example and let's calculate the speed of the electrons. Now we are given this information. We have a copper wire with a diameter 3.2 millimeters. And it carries a current 5 amperes. So the question is, what is the drift velocity? We know already the expression of the current. The current will be the charge density multiplied by the drift velocity multiplied by the area. Well, what is the area? Well, pi r squared, so it's just pi times 3.2 millimeter over 2 squared. This is the area we have. Now, the current divided by area, this is also given a name. This is called J, the current density. Which is E times N times Vd. One reason why we define the current density is that if you look at over here, it doesn't depend on the general shape of the conductor. It depends on the density at which you are calculating the current density and the drift velocity at that point. Anyway, so if we define that quantity, we have the area, we know the current, and the current density, if you put in the numbers, this is 6.2 times 10 to the power 5 amperes per meter squared. This is the current density. We need to determine what N is, what the number density. It's made of a copper, and we know the mass density of copper is 8.9 times 10 to the power 3 kilograms per meter cube. This is the mass density. The weight of a copper molecule, so it's, the molar density, atomic mass, is 63.5 atomic units. Well, it's more or less the carbon atom has 12 atomic mass, has a mass of 12 U. That's how we define this U. Or you can say that a copper piece of weight 63.5 grams has how many copper atoms? 6.02 times 10 to the power 23 copper atoms. This is the Avogadro's number. This is how we define the Avogadro's number. If you know the atomic mass of a material, in this case it's copper, 63.5 U. So if you have 63.5 grams of that material, it contains this much, the Avogadro's number of atoms. So this should be enough for us to determine the number density. Let's say that the number density, almost enough, the number density of copper atoms. Let's assume we have 63.5 grams of copper atom, of 63.5 gram of copper. Well, we know the total number. So the number density will be the total number. This is the total number of copper atoms. What is the volume? Well, the volume is its mass, 66.5 grams, divided by the mass density, 8.9 times 10 to the power 3 kilograms per meter cube. This is the number density of the copper atoms. And again, if you just put in the numbers, this is 8.4 times 10 to the power 28 atoms per meter cubed. Of course, this is not the charge carriers. The charge carriers are the electrons, not the atoms themselves. But on the average, you can assume that every copper atom just contributes 1 electron to the current, to the free electrons that will create our current. So the number density will be equal to the number of copper atoms, which will be 8.4 times 10 to the power 28 electrons per meter cube. So in every meter cube, on the average, we will have 8.4 times 10 to the power 28 electrons that are free to move to create the current. Now let's go back. We know the current density. This is the current density. This should be equal to E, the charge of 1 electron, which is 1.6 times 10 to the power minus 19 coulombs, times the number density, which is 8.4 times 10 to the power 28 per meter cube, times the drift velocity. Well, the drift velocity will be 6.2 times 10 to the power 5 coulombs per meter square second, divided by 1.6 times 10 to the power minus 19 coulombs, 8.4 times 10 to the power 28 per meter cube. The coulombs will cancel this one. We will have a meters over there. So this is 6.2 times 10 to the power 5 meters per second divided by 10 to the power minus 8, more or less. This is 6.2 times 10 to the power minus 3 meters per second, if I didn't make a mistake in the computation, in the numbers. Six millimeters per second. Well, per second it just moves this much. Did I make a mistake in the numbers? Anyway, the book has a much smaller number, but even this is small enough. So when you turn on the electric switch, the electrons just move this much per second. So how come? You see, I turn it off. No, I turn it off. And the moment I turn it on, I have light over there. I mean, it's moving like 5, 10 meters at the instant, not just many minutes later. If the electrons are moving so slowly, how come I get light at the end of the room the moment I turn on the switch?
Because there are electrons throughout the whole length of the wires. So as soon as you flip the switch, all of them start moving.
Yeah, essentially that's the idea. So the moment we turn on the switch, we start creating an electric field. The electric field, the change in the electric field, let's say, it just moves at the speed of light. So the moment I turn on the switch over here, there is an electric field on that wire over there. And all the electrons start moving at the same time. Just like, again, just imagine a water pipe. It can be a very long. When you tilt it, the moment you tilt it, the water starts flowing. It doesn't wait for the water at the end to come to the bottom. So it's essentially the same idea over here. Any questions up to here? Well, the book has a number 0.01 millimeters per second. I mean, it doesn't really make too much of a difference. The end story is the drift velocity is actually very slow. Any questions? Okay, so here we have been discussing the batteries. It creates a constant potential difference between the 2 points. So this is called a direct current. Or DC. The current flows always in the same direction. And the potential difference between 2 points is fixed. So that's why it's just pushing it in the same direction all the time. But if you use the plugs over there, they are not direct current, they are what is called alternating current. Or AC. Now in alternating current, the potential difference between 2 points is not constant. As a function of time, it just alternates between positive and negative values. This is how it will change with time. So you can write the velocity, the potential, as a function of time will be some V0 times cosine 2 pi f times t, f being the frequency. Are you familiar with the concept of frequency? So it's how many times it changes per second. In Turkey, for example, we have, do you know the frequency of the electricity we use? It's 60 hertz. So the 60 or 50? Let me look at the battery. Anyway, it doesn't say. It should be something like 50 or 60. So it will be constantly changing. Now the current will also be changing. We can still use the same expression. This will be V over R. So it's V0 over R times cosine 2 pi f times t, or I0 times cosine 2 pi f times t. This I0 is what is called the peak current. It's the maximum value of the current. It doesn't always have the same value. It goes up and down. It even changes direction. It starts from I0, goes negative. Negative current just means it's just moving in the opposite direction. So it changes between plus I0 and minus I0. Now, if you look at the power, well, the power for such a circuit, such a power source, will still be I times V. This is always valid. Whatever kind of source you have, power is always equal to I times V. Well, I is V0 over R times cosine 2 pi ft. V is V0 times cosine 2 pi ft. So the power is also changing with time. This is the power. The power is always positive. You see, in this very simple circuit where we have this alternating current and a single resistor, the power will still be positive. We will see other circuits where the power will be actually negative. The supply isn't providing power, but it is extracting power from the system. And the average value, this is more or less the average. The average value of power, which is usually shown by this bar, is V0 squared over R. The average of cosine squared is just 1/2. By the way, this is the same thing as the average of V squared divided by R, or the average of I squared multiplied by R. Because V squared is also cosine squared. V squared is V0 squared times cosine squared. The average of cosine squared is still 1/2. I squared is I0 times cosine squared. The average of cosine squared is still 1/2. And the average of the square is usually denoted as the RMS value, or under the square root. This is the root mean square. So you just take the square, take its average, and take the root. That's the RMS value. This you can think of it as the effective value in a sense. So the power, the average power, is given by the RMS potential difference multiplied by the RMS current, if you like. In this sense, it's as if, you see, this expression is as if the circuit was a DC circuit with the potential being the RMS potential and the current being the RMS current. Now we say that what is the voltage of the plugs that we use in Turkey? Which one is it? Is it V0 or VRMS? It's actually the RMS value, which is V0 over square root of 2. Is the peak power, the peak potential, is actually 220 volts times square root of 2. Which is something like 280 or 300, let's say, 300 volts. Something around that value. Any questions? Questions? Okay, let's give a 10-minute break, and then next hour we can do some examples.